So this one's kind of a two-part problem. A little extra bit here. So we have platinum and has a FCC crystal structure, an atomic radius of 0.1387 and atomic weight of 195. What is its theoretical density? Now you totally can look up in your textbook and it has a little equation for this, and you can just plug it in. But I want to show you how you get that equation, because if you understand how you get it, you'll have an easier time when you get something that you're not used to and you don't have an equation for. So density is simply equal to mass over volume. Mass over volume. That's supposed to be an M. I have beautiful handwriting. There we go. That's a little better. Now, how do I find mass? Well, it's not too terribly difficult. So first off, we're always doing things in terms of atoms. So atoms, they have an atomic weight that's equal to grams per mole. Okay? Grams per mole. And so if I want to, I can then figure out how many grams one atom is. How do I do that? By taking a mole of them. So I would say then, okay, well, if I have a mole of them, great. What's a mole? Well, a mole is Avogadro's number. So Na is going to be equal to 6.022 times 10 to the 23rd. And that's going to be atoms per mole. As I know, it can be anything per mole. It's just we're using atoms here. So let's figure out the mass of one atom. One atom. So that would be equal to my atomic weight times Avogadro's number. If I check out the units, that gives me, oop, I always do that wrong, my bad, sorry. Atomic weight divided by Avogadro's number. Like, how did you catch yourself? I did it based on units. I'm always checking the units here. So in the end, I should have grams per mole, or grams per atom. Grams per atom. There we go. Now, the second thing you have to ask yourself is, well, how many atoms are there in this cell? Because that's the volume I'm going to take. I need to know how many atoms there are. So for an FCC cell, there are 4 atoms. So therefore, the mass inside of this cell is going to be equal to my atomic weight times the number of atoms in that cell, all divided by Avogadro's number. That should do it. Yes, perfect. Now, let's plug this into here. So I get my density is equal to my atomic weight, which I know, the number of atoms, which I know, over Avogadro's number, which I know, times the volume, which I don't know. So I now need to get the volume. If I can get the volume, I can find out this theoretical density. So here's the second part of this problem. Let's go ahead and look at an FCC atom and see if we can figure it out. Now, an FCC atom touches along the faces. It touches diagonally along the faces. So if I had it look something like this, doing my best here. I should definitely have kept in my drawing class a little bit longer than I had. Okay, and one up here. That'll do, okay? Give me a break, I'm doing my best here. So if I have my, box here, it touches along the X's in that front of that box. That's why you need to know. When you're trying to find out the side lengths, you need to know that. So let's look at it just from that front plane right here and figure out the side lengths and then the volume in terms of the radius. So I can definitely just draw circles a lot more easily. That's not bad at all. So each of these sides is a length A. We can just call it the side length. Now we see here that it touches along the diagonal, and that's 1, 2, 3, 4 radiuses, so that's 4r. So with that, I can easily get a relationship between my side length and the radius. So let's do it. So 4r squared is equal to a squared plus a squared. And so that means that 16r squared is equal to 2a squared. I want to get a in terms of r, so we're going to solve for a. So a is equal to 8r squared, and I take the square root of it. That looks good. Fantastic. So A is equal to 2r square root of 2. Perfect. And my volume would just be that cubed. So that'd be 8r cubed times 2 square root of 2. Whoop. And my volume would therefore be equal to 16 square root of 2, all times the radius. Let's see. Cubed. Not bad. That works out pretty good. So long as I haven't made some horrible, horrible mistake. Nope, that checks out. So let's take that value and put it into my equation. Here we are. So I get my density is equal to, I'm going to go ahead and start plugging in numbers now. So the atomic weight, which is 195.08. Okay, that's good. Times the number of atoms, which is 4. All over Avogadro's number, which is 6.022 times 10 to the 23rd. And I'm going to need to plug in the volume now. I'm going to just erase this because I'm running out of space. Times 16 square root of 2. And then finally my radius cubed. As a note, I'm always doing things in like per centimeter cubed usually when I'm talking about density, especially for in grams. So I'm going to put it in terms of centimeters. Now my radius is 0.1387 nanometers. So you're confused about how I'm going to do that. Well, it's not terrible. If I'm putting that into centimeters, that would just be times 10 to the negative 7th. How do you get that? Because there are 100 centimeters in 1 meter, and there's a billion, or 10 to the 9th, or the 10 to the 9th, nanometers. That's where the conversion comes from. So I'd have 0.1387 times 10 to the negative 7th. If I plug that into my calculator, let's see what it comes out as. That comes out to be 21.46 grams per centimeter cubed. There you go. As a note, sorry, this right here is supposed to be cubed. Perfect. So we solved this one. Hopefully this helps you. Thanks for listening. I'll see you all next time. Bye-bye.